In 4.5 Part 2, we continue our study of integration by substitution with the substitution rule for definite integrals. If we let u equal g of x and du equal g prime of x dx, to get that the integral from a to b of f of g of x, g prime of x dx is equal to a new integral written in terms of the u variable, where we integrate from g of a to g of b, f of u du, and applying the fundamental theorem of calculus, we get capital F of the u variable evaluated from g of a to g of b. So let's take a look at an example to see how this works. Here we have the integral from 0 to 2 of x squared over the square root of quantity x cubed plus 1 dx. We definitely want to use substitution for this integral, so let's let u be the inside of this composite function in the denominator. So u is equal to x cubed plus 1. Then du is going to be 3x squared dx. So let's work on setting up our integral in the x variable first. We have the integral from 0 to 2. Now, since our u variable is the inside of this composite function, let's write that here as quantity x cubed plus 1 to the negative 1/2 power. Then we have that x squared dx, and I'm going to leave a little space there, x squared dx, because we recognize that we need 3x squared dx to get our du. So if we put a 3 in there, we have to counteract it with 1/3 out front. Now we can go ahead and do the substitution. We bring down the equal sign. We have 1/3 out front. That will remain out front. That's a constant. We have integral. Now for the limits of integration, we also need to do a substitution, because remember, for this integral, this is x equals 0 to x equals 2, but the new integral is going to be in terms of the u variable. So to do the replacement for the lower limit, let's come over here. We've got x and u. If x is 0, then u is going to be 0 cubed plus 1, which is 1. So in the new integral, the lower limit is going to be 1. Now the upper limit of the x integral was equal to 2, which means the upper limit for the u integral will have to be 2 cubed plus 1, which is 9. So we know that's going to go here for the upper limit. This expression right here, the quantity x cubed plus 1 to the negative half, is going to become u to the negative half. And then finally, 3x squared dx gets replaced with du. So now the integral is completely in terms of the u variable. So let me help you connect this to the rule. This part, integral from a to b of f of g of x, g prime of x dx, that's who this is. We took this original form and put it in a more workable form. So that's this part of the rule. Now this step here is actually this part of the rule, where we have the function in terms of the u variable, f of u, that's this one, u to the negative half, the du is the du, and the g of a means we took the lower limit and plugged it into g of x. So remember, u is g of x, so that's what we did here, where we took the lower limit of 0, plugged it in to g of x, and figured out what the u variable was. So in our case, g of a is this 1 right here, and g of b is g of 2. In other words, plug 2 into that inner function to see what the u variable would be, which is 9. So this integral here is this piece of the rule. Now what we need to do is apply the second fundamental theorem of calculus, where we get the antiderivative and we evaluate it at these two new limit values, g of a and g of b. Bring down our equal sign and the 1/3. We know that the integral of u to the negative half du is going to be u to the 1/2 over 1/2, which is like multiplying by 2. And we will have to evaluate that from 1 to 9. Well, this is equal to 2/3, bringing that constant out front. Then we would have 9 to the 1/2, so square root of 9, minus 1 to the 1/2, square root of 1. And there's something that I want you to notice here. We have never gone back to the x variable like we do with indefinite integrals. Notice in the rule here, you go ahead and do your evaluation staying in your new u variable. So for definite integrals, you never go back to x. And one kind of goofy way I like to help my students remember this is when it's definite, you definitely never go back to your x. So it's just a kind of a silly way that might help you remember that you don't go back to the x variable. You go ahead and evaluate the antiderivative at the new limit values for the u variable. So now we can continue to simplify here. Let's bring down our equal sign and the 2/3. And the square root of 9 is 3. And we have to subtract the square root of 1, which is 1. We know inside here, 3 minus 1 is 2. 2 times 2/3 is equal to 4/3. So as before, the outcome of a definite integral is a numerical value. And a big reminder here is for definite integrals, you never go back to your x. Just think of the goofy thing I said. When it's definitely over, when it's definite integral, you definitely never go back to your x. In this example, we are integrating from 0 to pi over 3 sine of 1/2 x cosine half x dx. So we have a couple choices to set up our u/du substitution because we know that the derivative of sine is cosine and the derivative of cosine is negative sine. So we could actually pick either one to be u. I'm going to choose u is equal to sine of 1/2 x because I know its derivative is a positive cosine and I don't have to keep track of a negative sign. So du is going to be cosine of 1/2 x, and then don't forget we've got chain rule that we have to take times 1/2 and then dx. So let's set up our integral in terms of the x variable here. We are integrating from 0 to pi over 3. We've got sine of 1/2 x, and we've got cosine of 1/2 x. And I'm going to leave a little space before the dx because when we worked out du, we see we're going to need that 1/2 in there. So if we put the 1/2 right here, we will have to counteract it with a 2 out front. Now we are ready to do our substitutions. So this will equal, let's highlight everything as we go. We have the 2 out front is going to come down as a 2 out front here because it's just a constant. We have our integral, and now we have to find our new limits of integration. So let's go off on the side here, and we have to change the limits. So the lower limit in the x integral used to be 0. So in the u integral, it's going to be the sine of 1/2 times 0. And we know the sine of 0 is equal to 0. So in the new integral, the lower limit is also 0. Now we have to change the upper limit, and we know in the x variable it's pi over 3. In the u variable, it's going to be the sine of 1/2 times pi over 3. The sine of pi over 6 is equal to 1/2. So the new upper limit here is going to be 1/2. Sine of 1/2 x, we are going to trade out for the u variable. And then cosine 1/2 x times 1/2 dx is going to get traded out for du. So now everything in the original integral has been highlighted and changed over to the u variable. And we can only do substitutions that we've written over here. The reason I can write u for sine of 1/2 x is because that's what we wrote, that they're equal. The reason I can take cosine 1/2 x times 1/2 dx and replace it with du is because they are equal. Same with these limits of integration. So now it's time to evaluate the integral. So this is going to equal 2. And the integral of u du is going to be u squared over 2 evaluated from 0 to 1/2. And let's remind ourselves that for definite integrals, never go back to x. We stay in the u variable and continue to evaluate only in the u variable. Now these 2's will cancel, and we will have to do 1/2 squared minus 0 squared using the fundamental theorem of calculus. And so our result is going to be 1/4. In this example, we have to integrate from 1 to 5 x squared times the square root of quantity x minus 1 dx. Let's let u be the inside of the radical function. So u is equal to x minus 1. Then we know that du is going to equal dx because the derivative of x is 1 and the derivative of 1 is 0. Now because our du is the same as dx, there's not a whole lot of manipulation of the integral that we have to do. So let's go ahead and start doing our substitutions. We'll integrate, and let's come back and do the limits of integration in just a minute. First up, we have this x squared going on, and we have to figure out what that's going to be in the new u variable. So we can take this equation, u equals x minus 1, and if we solve for x, we get u plus 1 is equal to x. So then that means when we have x squared here, it's going to turn into u plus 1 squared in the u integral. Here we have square root of x minus 1, and the x minus 1 can get replaced with u, so this is going to be times u to the 1/2 in the u integral. And we know the dx can get replaced with du. Now the only thing left to do are the limits of integration. We have to change them from the x variable to the u variable. We know that the lower limit for x is 1, and then for u, that's going to be 1 minus 1, which is 0. So the lower limit of 1 in the x integral changes to a lower limit of 0 in the u integral. Next, we have to change x equals 5, and substituting x equals 5 into the equation, we have 5 minus 1 is equal to 4. So we know that the upper limit for the u integral is going to be 4. So now everything from the original integral has been converted over to the u variable. Now we can't evaluate this integral as it is because we have a function times a function, and we can't integrate that. So we have to do some simplifying first. This becomes the integral from 0 to 4. We can square this binomial to become u squared plus 2u plus 1. We have to bring down the u to the 1/2, and we have to bring down the du. Next, we need to distribute this u to the 1/2 into all three of these terms in here. So now we have the integral from 0 to 4 of u to the 5/2 plus 2 times u to the 3/2 plus u to the 1/2, close the parentheses, du. Now we're finally ready to integrate. So this is going to equal, we take each of these, and because they have plus signs between them, now we can integrate them on their own. So integrating u to the 5/2 du, we're going to get u to the 7/2 over 7/2, which is multiplying by 2/7, plus 2 times u to the 3/2 will integrate to u to the 5/2 over 5/2, which is multiplying by 2/5, plus u to the 1/2, which will integrate to u to the 3/2 over 3/2, which is multiplying by 2/3. Now we have to take this whole thing, put it in a big bracket, and evaluate that from 0 to 4. Then that's going to equal 2/7 times 4 to the 7/2 plus 4/5 times 4 to the 5/2 plus 2/3 times 4 to the 3/2 minus, we have to plug in the lower limit, which would be 2/7 times 0 to the 7/2 plus 4/5 times 0 to the 5/2 plus 2/3 times 0 to the 3/2. Now this whole second term here is going to be 0, and to evaluate this first term, we punch that into our calculators. And why don't you pause the video right now and try plugging that into your calculator to make sure you're comfortable getting this result. Then restart the video when you're ready to check your answer. If we round to the 10th place, this is approximately 67.5. And that's if we go to the tenths. Here we will solve a differential equation involving substitution. In this example, we have to solve the differential equation dy dx is equal to 2x times the square root of the quantity x squared plus 3. Now we can write this in differential form, so we would have dy is equal to 2x times the square root of x squared plus 3 dx. Now we can integrate each side. So we take the integral of dy, and that's going to be the integral of 2x times the quantity x squared plus 3 to the 1/2 dx. Now remember that we will get a plus c from the left-hand side and another plus c from the right-hand side, and what we will do is combine them both into 1 plus c on the right-hand side. So we will combine the two constants of integration into 1 plus c on the right-hand side. So then when we integrate dy, we will write it as y. Normally it would be y plus c, but we're going to combine those constants of integration. Now on the right-hand side, we aren't quite ready to integrate because we'll need to do a substitution. So if we let u equal x squared plus 3, then du would equal 2x dx. And we can actually just reorganize this into the integral of x squared plus 3 to the 1/2, and then I'll take the 2x and put it over with the dx. And now it's a pretty easy substitution to do. We have y equals the integral. This quantity, x squared plus 3 to the 1/2, becomes u to the 1/2. And then the 2x dx becomes du. So now we have y equals u to the 3/2 over 3/2. And now we will finally put our plus c. And remember, we're going to get a constant of integration from the left-hand integral, call it c1, and a constant of integration from the right-hand integral, call it c2, and we're just combining those two constants together into a constant we're calling c. Now, because this is an indefinite integral, we do have to go back to the x variable. So this becomes y is equal to 2/3 times the quantity x squared plus 3 to the 3/2 plus c. And this is the solution to our differential equation. Next, we look at integration with even and odd functions. Let f be integrable on the interval -a to a. So notice this is a symmetric interval, meaning we go as far in the negative direction as we do in the positive direction. We get two cases. If f is an even function, then the integral from -a to a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. Now remember what it means to be an even function. The test is you look at f of -x, and if f of -x is the same as f of x, then you know that you have an even function. And that means it's going to be symmetric to the y-axis. So when you have an even function and you're doing a symmetric integral from negative a to a of f of x dx, you can choose instead to just look at the positive side from 0 to a, find that integral, and double it. Now, the second case is if f is an odd function, then the integral from negative a to a of f of x dx is equal to 0. It's very powerful. And remember, the test for odd functions is if you plug in f of negative x and it's equal to negative f of x, then you know that you have an odd function. And odd functions are symmetric to the origin. So next up, we will explore a couple of simple graphs to help you understand how these two rules can work to make finding integrals much easier to do. In this example, consider f of x is equal to cosine x. We have the graph here, and the first question is f even, odd, or neither? Now we notice that this graph is symmetric to the y-axis. Another way of saying that is that f of negative x is equal to f of x. Now make sure you understand what this means. This is saying the y value at negative x is exactly the same as the y value at x. And looking at this graph, you can see that the y value at negative pi over 4 is exactly the same as the y value at positive pi over 4. So cosine is an even function. The next question asks, how does the area under f from negative pi over 2 to 0 compare with the area from 0 to positive pi over 2? Well, if we look at these two areas, the first one from negative pi over 2 to 0, that would be here, this area. And then we're trying to compare that to the area from 0 to pi over 2, which is this area. And just looking at them, you can see that they're the same area because the graph is symmetric to the y-axis. So the area from negative pi over 2 to 0 and from 0 to pi over 2, those two areas are equal. And that's why when we are doing a symmetric integral of an even function, remember cosine is even, instead of having to integrate from negative pi over 2 to positive pi over 2, from here all the way to here, what we can do instead is integrate from 0 to pi over 2 and then just double that. And the only time you can do that is if you have an even function, because you know the area to the left of the y-axis is going to be exactly the same as the area to the right of the y-axis, so you can just do that right-hand side integral and double it. Now this is going to be 2 times the integral of cosine of x dx, which is sine of x, evaluated from 0 to pi over 2, which is going to be 2 times the sine of pi over 2 minus the sine of 0, which is equal to 2 times 1 minus 0, which is 2. So whenever you have an even function, meaning f of negative x equals f of x, or when you're looking at its graph, you see that it is symmetric to the y-axis, instead of doing the integral from negative pi over 2 to positive pi over 2, we can double the integral from 0 to pi over 2. And plugging in 0 is almost always an advantage because it's often a simpler value to plug in and evaluate. In this example, we consider f of x equals sine of x. We have its graph, and we want to know, is f even, odd, or neither? Now, when we look at this graph, hopefully you recognize that it is symmetric to the origin. And another way of saying that is that f of negative x is the opposite of f of x. And so what this means is the y value at negative x is the opposite of the y value at x. And that's pretty easy to see. Once again, let's look at and compare the y values at negative pi over 4 and positive pi over 4. At negative pi over 4, here's the y value, which we know is negative radical 2 over 2. And at positive pi over 4, here's the y value. It's positive radical 2 over 2. So those two are symmetric to the origin, and that makes sine of x an odd function. Now, in this problem, we are being asked, how does the area under f from negative pi to 0 compare with the area from 0 to pi? So let's look at those two areas. From negative pi to 0, here's the area between the x-axis and the curve. And from 0 to pi, here's the area under that curve. And we notice that those two areas are just opposites. The shapes are the same, but the net area here is going to be negative, where the net area here is positive. Other than that, they're exactly the same magnitude. And so that's why the integral from negative pi to pi of sine of x dx is going to be 0. And the reason is because sine is an odd function. When the limits of your integration are a symmetric interval and you're integrating an odd function, the area to the left of the y-axis is going to cancel out the area to the right of the y-axis, and your integral is going to be 0. In this example, we will use the even-odd properties to simplify and evaluate the definite integral. Here we have the integral from negative 2 to 2 of the quantity x to the fourth plus x to the third plus x squared plus x dx. Now we want to separate this integral into two parts, one for the even functions and one for the odd functions. And we know we want to do this because we recognize that we have a symmetric interval for the limits, and easy to recognize that we have some even functions here and some odd functions here. So this becomes the integral from -2 to 2 of x to the fourth plus x squared dx plus the integral from -2 to 2 of x cubed plus x dx. We know these functions are even because f of negative x returns the same value as f of x. We know these functions are odd because f of negative x would return the opposite of f of x. And with polynomial functions, any exponent that is even is going to return an even function. Any exponent that's odd will return an odd function. So now we know this, we can use the rule for even functions, and for this we can use the rule for odd functions. So that means to do this first integral, instead of integrating from -2 to 2, we can do 2 times the integral from 0 to 2 of x to the fourth plus x squared dx plus, because this is an odd function on a symmetric interval, then this integral is going to be 0. So we just got rid of a whole bunch of work. Continuing, this is going to equal 2 times x to the fifth over 5 plus x cubed over 3 evaluated from 0 to 2. Continuing to simplify, this will equal 2 times 2 to the fifth over 5 plus 2 to the third over 3 minus 0 to the fifth over 5 plus 0 to the third over 3. And you can see why we love plugging in x equals 0, because this whole part is 0. So now, if we grab our calculators and evaluate this one, we will get 272 over 15. So you can see the power of being able to use the properties of even and odd functions. All the odd functions that are integrated on a symmetric interval just go to 0, and the even functions, we get to double the integral from 0 to the upper limit, which means we get to plug in 0, which also makes the calculating easier. So it's a really powerful tool to use. In this example, we're given that the integral from 0 to 5 of f of x dx is equal to 3. And then we are being asked to evaluate a series of other integrals based on whether f is an even function or f is an odd function. Now we don't know what the graph of f of x looks like, so what we can do is use the fact that the integral from 0 to 5 of f of x dx is equal to 3. And we could choose to draw a picture of a graph and label the area under f from 0 to 5 to be 3. So for example, we could draw some simple curve like this and say that this area from 0 to 5 is equal to 3. And that's going to be the same whether f is even or f is odd. So we can draw the same picture over here and say from 0 to 5 the area is 3 using this integral that was given to us. Now what we want to do is draw these pictures based on whether f is even, draw this one, or f is odd, draw this one. So I want you to pause the video for just a second. Try drawing the rest of these graphs. Draw this one so that f is an even function, draw this one so that f is an odd function, and then restart the video when you're ready to check your answers. Now if f is even, we know that f of negative x has to equal f of x, which means the graph has to be symmetric to the y-axis, which means the rest of the graph would have to look like this. And we can see this area matches that area and must be 3. If f is odd, then we know that the graph is symmetric to the origin, or in other words, f of negative x is the opposite of f of x. An easy way to draw a graph symmetric to the origin is to think of flipping it over both axes. So if we took this graph and flipped it over the x-axis, it would land here. And then if we took that and flipped it over the y-axis, it would land here. Now this net area is going to be negative 3. And now we can use the pictures that we made to help us answer these questions. We'll use this graph for when f is even, and we'll use this graph for when f is odd. So I want you to pause the video again and answer these questions, and then restart the video when you're ready to check your answers. First up, we have to evaluate the integral from -5 to 0 of f of x dx. Now if f is even, we can see from our diagram that area is just 3. And if f is odd, we can see from our diagram that area will be -3. The integral from -5 to 5 of f of x dx, we can see is going to be 6 if f is even, and it's going to be 0 if f is odd. Now here, we have to integrate from -1 to 4 f of x plus 1 dx. Now you have to think about what this means is happening to the graph. And we know that that means it's going to shift left by 1. So if we were to take the whole entire graph and shift it left by 1, then that means this part, instead of going from 0 to 5, is going to shift to the left and go from -1 to 4. And we know that that area is going to be 3. So this first answer is 3, and the second answer is also 3, because that part of the graph is the same whether f is odd or f is even. Now here we have to evaluate the integral from -5 to 0 of negative f of x. Now that negative sign means it flips over the x-axis. So what you have to do is look at each graph. In the case of the even function, we have to take the part that's from -5 to 0 and flip it over the x-axis. So now it would be down here, which means we're going to get -3. For the odd function, once again, we have to take the part that's from -5 to 0, flip it over the x-axis, which now means it would be up here. So this one's going to be positive 3. This last one says take the integral from 0 to 5 of negative f of x dx. So if we look at the part from 0 to 5, that's this part right here. If it flips over the x-axis, that means it's going to be down here, and our integral would be negative 3. Now for the odd function, that part of the graph is the same, so if we flip it over the x-axis, it's going to go below, and it would also be negative 3. And that's how, when we are given a definite integral, we can use some quick sketches that we make to evaluate integrals about the function, even when we don't know what the function is, using the properties of even and odd functions.